Welcome to all of you. In this lecture, we are going to continue with the ray theory transmission, the remaining topic, numerical aperture. Let us first go through what is this numerical aperture. This numerical aperture provides the relationship between the acceptance angle and the refractive indices of the three media involved, namely the core, cladding, and the air. Now let us first understand this diagram. Based on this diagram, we are going to have a small derivation for the numerical aperture. So this is the complete optical fiber. This is the core part and this is the cladding part as well as this is the cladding part. The core is having the refractive index of N1. Cladding is having the refractive index of N2. Now this is the air medium. The light is entering from the air medium to the optical fiber through the axis of the optical fiber, and we are going to consider that the refractive index of the air is equal to N0 and the light is entering with an angle of theta 1, and here it is going to be refracted at an angle of theta 2. After that it will get total internal reflected, then it will move out. So at this point the angle is phi and here also the angle is phi, right? So just note down A, B, C are the 3 points. So this point, the entry point is called A, and the location where the light gets total internal reflected or the interface between the core cladding. So this point is P, and this axis which meets the center of the optical fiber is considered as the location C. So try to understand these notations. Based on these notations, we are going to have a small derivation. Okay, so these 2 points are going to refer with the points that just now I referred. Now getting into the actual derivation part. Now assuming the entrance phase at the optical fiber core to be the normal to the axis, then considering the refraction at air core interface. So remember we are considering air core interface, then by Snell's law it will become N0 sin theta 1. So N0 is the refractive index of the air, theta 1 is the angle of incidence, then that will be equal to N1 sin theta 2. So N1 is going to be the refractive index of the core, theta 2 is the angle of refraction. So now here we can observe, so this is the theta 1 and this is for the theta 2. So this is the angle of incidence theta 1 and this is the angle of refraction theta 2. So now here we can observe that by considering the triangle AB as well as C. So there are 3 angles we can identify, theta 2, then phi, and then one more is the right angle. Now if we identify the angle phi over here, then it can be given by this pi by 2 or 90 degree minus theta 2. So that has been represented over here. So phi can be represented by pi by 2 or calculated by using pi by 2 minus theta 2. Now rearranging this expression, finding the representation for theta 2, we can simply write it as theta 2 will become equal to pi by 2 minus phi, right? So in the equation 1 that has been shown previously, in that equation theta 2 is present on the right hand side. By replacing theta 2 by its equivalent value, it will become N0 sin theta 1, left hand side as it is, the right hand side will become N1 sin, instead of theta 2 it is pi by 2 minus phi. Call this as equation 3. Now left hand side remains as it is, right hand side it will become N1 cos phi. Sin pi by 2 minus phi is equivalent to cos phi. Therefore, it is replaced by this cos phi. call this as equation 4. Now we are having a relationship in the trigonometry, that is sin square phi plus cos square phi is equal to 1. Now we are having the term cos phi. Identify the relation for cos phi using this representation. So by that we get n0 sin theta 1, left hand side as it is, will be equal to n1 of 1 minus sin square phi whole to the power of half. So call this as equation 5. So now when it comes to the concept of limiting case, so that is total internal reflection, so phi becomes equal to the critical angle. So now we can replace phi by phi c, the critical angle. So for a core cladding interface, also limiting case of theta 1, so that is angle of incidence from air medium to the optical core medium, so that is theta 1, will become the acceptance angle theta a. So now considering this limiting case, now we can replace theta 1 present here by theta a. So now this will be completely represented by n0 sin theta a will be equal to n1 square minus n2 square whole to the power of half. So remember, we are considering the limiting case, the critical angle and then the acceptance angle. By making use of these two factors, the expression will reduce to this form. Now the equation 6. So apart from relating to the relating acceptance angle to the refractive index indices, it also serves as the basis for the definition of the numerical aperture. Therefore, so the definition of the numerical aperture is it's a relationship between the three mediums, core, cladding and the air, and that is what we have achieved here also. So n1 with respect to core, n2 with respect to the cladding, and then this one with respect to the air interface, air and the optical fiber interface. So all these three relationship, we have the relationship between these three has been derived, that is nothing but the numerical aperture. Therefore numerical aperture is given by, it will be equal to n0 sin theta a will be equal to n1 square minus n2 square whole to the power of half. Consider this as equation 7. So this is what the required relationship of the numerical aperture. Now in a special case, so numerical aperture may also be given in terms of the refractive index difference represented by delta. So it is given by delta is equal to n1 square minus n2 square divided by 2n1 square. So in a special case, so it can also be represented as n1 minus n2 divided by n1, since delta is a small value. So it is too much less than 1. Therefore, so instead of this realization, we can also refer that as n1 minus n2 divided by n1. Now combining these expressions, we can write the numerical aperture as n1 into 2 delta to the power of half. Now let us go through one or two problems related to the fact. Now first problem statement: a silica optical fiber with a core diameter large enough to be considered by ray theory analysis has a core refractive index of 1.50 and cladding refractive index of 1.47. Determine, first one, the critical angle at the core cladding interface. Second, the numerical aperture of the fiber. Third one, the acceptance angle in air for the fiber. So first note down the given parameters. Two parameters are being given, the refractive index of the core and the refractive index of the cladding. Note down those two. So core refractive index given by n1 is equal to 1.50, always higher. Cladding refractive index n2 is 1.47, must be lower than that of the core. So now start with the first one, the critical angle phi c calculation. The critical angle phi c is given by the formula sin inverse of n2 divided by n1. n2 and n1 are the known parameters. Make the substitution. We are going to have this answer. Second one, calculation of the numerical aperture. The numerical aperture is given by n1 square minus n2 square whole to the power of 1 by 2. So we know these two parameters. Make a substitution, resolve it. We are going to have the answer of the numerical aperture. Now coming to the acceptance angle, theta A. So theta A is given by sin inverse of the numerical aperture. So numerical aperture has just now calculated, substitute it, and we are going to have the corresponding answer for that. Now getting into the one more problem where we are going to use the difference in the relative difference in the refractive indices. The statement, a typical relative refractive index difference for an optical fiber designed for long distance transmission is 1%. Estimate the numerical aperture and the solid acceptance angle in air for the fiber when the core index is 1.46. Further, calculate the critical angle at the core cladding interface within the fiber. It may be assumed that the concepts of geometric optics hold for the fiber. First note down the parameters. So given the relative refractive index difference, that is equal to delta, is 1%. So that is equal to 0.01. The refractive index of the core is given, that is n1 is equal to 1.46. So two parameters need to be calculated, that is estimation of the numerical aperture. Second one is the calculate the critical angle. So these two are required to be calculated. Start with the numerical aperture. So for the numerical aperture, we are having a formula saying n1 into 2 delta to the power of 1 by 2. So n1 is a known parameter, delta is a known parameter. Make the substitution. We are going to have the numerical aperture as 0.21. So one parameter is calculated. Second one, we need to calculate the critical angle. Okay, now calculate the critical angle. So now the relative refractive index difference is given by delta, that is equal to n1 minus n2 divided by n1. So by making a little simplification of this one, we can write it as n1 by n1, that is 1, minus n2 by n1. So that is what is being written over here. Now rearranging this complete expression, we can write as n2 by n1 is equal to 1 minus delta. Now delta is a known factor, substitute for it. So n2 by n1 is equal to 1 minus 0.01, that will be equal to 0.99. So we have got the value of n2 divided by n1. So the formula for critical angle is phi c is equal to sin inverse of n2 divided by n1. So n2 divided by n1 is just now calculated. So directly make the substitution 0.99 over here, and we are going to get the answer for the critical angle phi c. Thanks for joining.